paper, which they use the rotation measure of the PRS, the rotation measure of the FRB and the luminosity of the PRS. So they use a famous relation called as YLZ relation, which relates both the parameters, the rotation measure of the FRB and the luminosity of the PRS associated with it. And using this relation, they calculate H naught. So basically, if you follow FRB science, they use a traditional method where they calculate H naught from dispersion measure and redshift relationship. Here they have proposed a novel technique where they use this so-called YLZ relation, which is an empirical relationship between the rotation measure of the FRB and the luminosity of the PRS. So as of now, they have only 4 samples which has this association between FRB and the PRS system. And using this 4 FRBs, they calculate the H naught to be around 86 with the given error at a 68% confidence level. Still, this value is within 2 sigma level compared to the CMB and the local distance method. So, however, they have performed Monte Carlo simulations to show that if we increase the sample size around, let's say, 400 FRB PSR systems, they say that the relative uncertainty is reduced to around 4.5 percentage, which means the error is reduced around like 4.5 percentage, up to 4.5 percentage. In addition to that, what they have done is they combine both the methods, the current existing DMZ relation method and the newly proposed YLZ method. So they combined both the methods. They took 100 FRB in this case and 100 FRB in the second case, and they combined it to calculate the H naught. And they show that this new method of finding H naught has a relative uncertainty of up to 2.9 percentage. So I think we can move on. Yeah. So this equation one is the famous YLZ relation, where you can see that the luminosity of this particular PRS is connected to the rotation measure of the given FRB associated with it, and we all know that we can calculate the luminosity distance from the observed luminosity. So we use the equation 1 to find out to relate it with the rotation measure. So from this we can see that we can calculate luminosity distance with the help of rotation measure for this system. And this part is for the observational part. So they compare this with the theory. So we all know that from FRW cosmology, the luminosity distance is related to the Hubble's constant H naught, and it is a function of redshift z. So using this, they calculate H naught and they compare. And what they did is like they fitted the observational data with the theoretical curve, and they used Gaussian likelihood to calculate the model parameters such as H naught here. So basically, they used they fitted the observed parameter and the theoretical parameter to calculate H naught. Here you can see the equation figure 1. Figure 1 gives us the redshift distance modulus plot for this particular system. The orange data point corresponds to the observed 4 FRBs, and the blue data points corresponds to the curve. The blue data points are the data taken from this particular paper, Suzuki et al., where they use supernova light curve. Maybe I can show the plot here. So you can see that this is the paper that they mentioned. Here they use the supernova light curve to calculate the redshift, to calculate the distance modulus versus redshift. So they compare this with the FRBs that they use, and this gray region corresponds to the 1 sigma error for this blue curve. So from this, they estimate the H naught to be around 86 with the given error. And from the figure 2, you can see that the peak of this is a probability density function. I mean, the peak of this H naught distribution is within two sigma level confidence for the both CMB as well as local distance ladder method. So this shows the novelty in their approach. You can, even though they only used 4 samples, they are still within 2 sigma level confidence. So in order to improve the significance, what they did is like they try to simulate 400 mock FRB sources with the given parameters here, with the given parameters, and they calculate the relative uncertainty in H naught. You can see that they achieved a precision up to 4.5 percentage when they simply improve the number of samples from 4 to 400. So later they combined both two methods, PRS rotation method and the traditional one. So here you can see they created 100 samples for they generated 100 samples for the comparison. Here you can see that the figure 3 is uh, the figure 3 is the plot where you can see there are 400 FRBs that are generated using this Monte Carlo simulation to get this H naught. So this is the distance modulus plot for that 400 FRB sources. And now once they created the simulated this mock FRB data, they try to use both the methods. So first, basically, they use the well-known dispersion measure relation, and in this part, we know that they assumed the dispersion measure IgM component and dispersion measure host component, which is given in the equation 7 and 8. So for the assumption of DMIGM, they obtain the relation from the McCart paper. This is the likelihood function mentioned in the McCart paper. And for the case of DM host, they assumed a likelihood function which follows a log normal distribution. So combining this, they have obtained a general likelihood function which is given in the equation 10. So basically, this general likelihood function obeys well when both the DM IgM and the DM host is somewhat consistent. So using this, they calculate the combined likelihood for DM in the case of dispersion measure and the rotation measure from the equation 11. So this calculate the this calculate the using this we can calculate the H naught in the later on section. This is the important equation. So using this we can calculate the H naught in the later on section. So for that, so basically what they did is before going on to calculating the combined H naught, they first calculated the H naught only using the DM data with the help of DM data mentioned in this Young et al. Paper. Mentioned in this Young et al. Paper, but here they used both two models of DM Milky Way. One is from YM16 model and one is from NE 2001 model. You can see the figure 5 gives us the in the figure 5 this blue color shaded region and the orange color shaded region gives us the two different values of H naught corresponds to two different models of DM Milky Way. So in the case of in the case of YMW16, they derived the value to be 67.55 with the given error, and in the case of NE 2001, they derived it to be around 71. So in addition to that, when they incorporate this rotation measure method with the conventional method, however, when they take only the observed data, they found out that there is no big significance because the observed number of samples is very less to produce any statistical effect. So you can see this green color curve in the figure 5. The green color curve and the red color curve corresponds to the rotation measure added to both YM16 and NE 2001 models. So what they did in order to find out the statistical significance here, they simulated 100 FRBs with the help of DM relation, and they simulated 100 FRBs with the help of the YLZ relation, which is given in this purple and the brown box line. So this
Your time.
sorry sorry hello.
Your time. Please try to summarize.
Yeah, I'm going to conclude. Yeah. So this purple and the brown boxed lines give us the combined relation, and when they try to simulate this relation, they found out that the H naught uncertainties are up to 2.9 percentage. So yeah, in conclusion, we can say that this method is a novel method where if we try to improve the number of sample, we can reduce the error percentage up to 2.9. However, we need to note that there are two systematics involved here. One is the observational uncertainties in rotation measure, as well as this parameter. They assume a model. I mean, like they assume a log normal distribution here for this parameter, modeled parameter. So this could bring some systematic effects here. So if we can able to solve these two kind of effects, then they believe that this could be a novel method of finding H naught. I think I'm done. And I think I'm completed.
Thank you, Vignesh. Are there any question?
What is the physics of this relation? Why this rotation measure and then luminosity of the source is related?
Uh, I think they didn't mention why this is related, but due to the magnetized, they said that the this relation can be explained from this fact that these only show in magnetized environment. I am not sure why it is
Can
related.
you explain equation one and equation two of this relation? Why
Ah.
the YLZ paper?
Uh, so this equation one is a relationship between the rotation measure of the particular
No,
FRB.
not this paper. But then
You mean
why paper? That
sorry, Professor, I didn't read that paper. I didn't read that paper. Maybe
maybe
if I can
tomorrow.
read it. Yeah, I try to read it, I try to read it, Professor.
Okay, thank you.
Vignesh, I have also minor comment.
Sure,
I
Professor.
think this is basically same as say standard candle, right?
Yes,
Then
Professor.
in that way, I think this YLZ relation is using luminosity. Then
Yes.
to calculate luminosity, they need to assume cosmology. So therefore, I think there should be cosmology assumed in YLZ relation in that
Uh,
paper.
maybe I
Therefore,
can check. Maybe I
I
can.
so that means this YLZ relation should be calibrated with say either local distance radar or CMB.
Hmm.
Therefore, their result in this paper is
Mm-hmm.
probably affected by this calibration. So
Calibration
therefore,
wise.
original calibration in YLZ relation. Because if you
Hmm.
change cosmological parameters, then luminosity changes, right? Because
Yes,
luminosity
yes,
distance
yes.
changes. Therefore, original this YLZ relationship already include cosmology, I think. Therefore,
Hmm.
I don't know how they discuss this kind of circular argument,
Hmm.
right? So
Hmm.
therefore, they need to calibrate with something, I think.
Hmm. Maybe I can check this in this YLG paper.
Hmm. Then,
So
then
I didn't got the time to check this paper. Maybe I can check
I
it.
actually, this method is very interesting, but then how
Ye-
to calibrate is say if you calculate with type and supernova, then answer goes to type and supernova. Then if you calculate with CMB, the answer goes to CMB. So therefore,
Towards CMB.
I wonder
I understand.
how they discuss this kind of things.
Maybe I can check in this paper how they got this
Yeah.
relation. Sure.
Yeah. But I think idea is interesting because this new
Sure.
standard candle.
Yes.
Okay, so thank you, Tetsuya-san and Tomo-san for the question and comments. So I think it's time to move on to the next person. Who want to go next? So maybe Songjin.
Okay. I'll share my screen.
Yes.
This paper talks about large language model for astronomy. So their model is trained on many archive papers from 2004, along with many QA. So the main high performance AI model specifically for astronomy. So as you know, there have been many large language model like ChatGPT-4, Gemini, Llama, Grok, something like that. So these general LLM, large language models, can be used for many different multi-purpose, but it may lack deep knowledge in specific fields like astronomy. So this paper aims to develop a highly specialized large language model. The name is this Astro-ph Llama 3.18b. So the performance level is GPT or like. So they wanted this model achieves this kind of level. But actually, in astronomy, this kind of high performing models is been achieved.
Sonja, I'm so sorry for interrupting. I think today the voice is not clear using that microphone. So are you close enough to the microphone?
Yeah, I think I'm really close.
But then your voice sometimes stops, then it's hard to hear. Maybe you can use your laptop for microphone.
Can I?
Is that possible?
How about now?
This is much better. Sonji,
clear
maybe
now?
could you say it again? Hello.
How about now? Is it clear?
This is much better.
Okay. So shall we go like this? Yeah. Okay. So, so their purpose is to develop a highly performing GPT-4 like large language model, like specifically for astronomy. So the name is this Astro-ph Llama 3.18b. So AI can help astronomers when astronomers trying to brainstorm new ideas, and it could review tons of complicated papers super quickly, and even help data analysis. And beyond that, all these things can be processed automatically. Practical difficulties is kind of reaching to GPT-4 level
the difficulties are extensive experimentation, optimization. So this requires, large-scale model training and, computer costs and data requirements. So you have to keep the model size manageable, and at the same time, you have to maintain high performance. So in this work, they used a base model first. They have a base model and astronomy data, and then they try to clean the data and fine tuning. Yeah, this is the main procedure. So what they used is Meta's Llama model. I think this is kind of latest model. So they used the Llama 3.18b model. They say even though it's not open source, but compared to the others, there are fewer restrictions. So you can use it for research or education, but for the commercial purpose, you need a permission from Mark Zuckerberg. So, and then training data are archived paper from 2007 to 2024, and also 30,000 articles in Wikipedia, and also 800 astronomy textbook. This is training data, and supercomputer, they say it's one of the strongest one, ORNL. It's Oak Ridge National Laboratory in Tennessee. So they used this supercomputer, and they say 15,000 GPU hours. And then there's a data cleaning process. So they try to assign scores and remove the low quality data. And then supervise the fine tuning. They this is not just a simple obtaining the knowledge. It has to follow the instructions and prepare the best answer effectively. So that's why this fine tuning is needed. So they created a Q&A pair from the data. So 11 million synthetic Q&A pair, they prepare this. And then they checked if they are correct. And also they checked if each pair is understandable without any other additional external context. And they checked if the question is important and valuable for deeper understanding, and then overall quality checks. So, and then they prepared kind of some examples, kind of question, answer, and score, and then explanation, this set. They prepared this set and gave this set to their model. And then after that, they gave only Q&A pair. Then this model had to complete the other part, the score and explanation part. So through this kind of fine-tuning process, they excluded some of them, and only 8.8 million high-quality Q&A pairs remained. So these are examples. So some nice Q&As are left. So this process helped the AI develop kind of the ability to understand questions and provide nice answers. And after that, they tried to merge with another Llama model, because this model sometimes suffering from the conversation and Q&A problem. So they combined the two language model, this model and another model, Meta's instructor model. So instructor model is done extensive additional training specifically to improve the conversation and instruction following kind of ability, especially for Q&A process. So they merged this model. For the conversation, and another part is astronomy. And the most important figure is figure 3. Though this figure shows how their model works. So they say, this one, the black star Astro stage Llama 3.1 outperforms other language model. You can see the empty star here. These three models are astronomy LLM model. And then the others are just general large language model. So it shows, this is a performance comparison.
So how do they evaluate the score?
You mean this score? They say Astrolab they have Astrolab benchmark. So this is test benchmark.
Yeah, so I'm asking how this benchmark works.
I'm sorry, I haven't checked that part. I don't know how Astro M Lab 1 works. I don't know. Yes, yes. So you know ChatGPT-4 is here. So x-axis is the cost, and y-axis is performance. So it's 10 times cheaper.
Can you ask this model how they evaluate its own performance?
You mean Astro-ph? As benchmark consists of a diverse astronomy-related question. So maybe this is Q&A test, I think.
Then, so when the AI returns the answer, how do they evaluate these answers?
Correct. Yes. I just tried to understand the rough structure of the paper, but I didn't check the details. But here, maybe they have a this is not the details.
Did they show some example of a difficult question and then how they answer that?
Difficult question. So I don't know. When difficult question, this figure one, actually they cut here, and this part is actually difficult part. They in the fine tuning, they only chose some a part which their their large language model understand. So if you give some very difficult question, the large language model cannot answer, or shows some weird behavior, and then so this perplexity means this large language model understand the question, and then they cut this part. So they chose only this part, but I don't know how they.
What is this cut is for? What's the purpose of this cut?
Mm, so low perplexity means this large language model understand the question very well.
Really?
Yes.
How
Yeah,
do
or-
you know?
I don't know. According to the paper.
I mean, does the paper show that? I don't think so. This is for training, no?
Is a part of training.
Oh, this is just to prepare training set, no?
Yes, yes.
So this is nothing to do with AI can answer the question.
Yes, yes. Let me check the details.
Okay, so I will start. So, thank you, Songji, and it's time to move on to Tetsuya-san.
Sure. Can I ask one more question? Sorry.
Sure.
I wonder, say, this is, say, asking Q&A, right? And then,
Yeah.
so what can we use this for? Say, practically. Say, for
Practical.
example, if there is a clear answer, then it's maybe useful. Say, in introduction, for example, introduction paper. So we need to have some understanding or background, right? So then I was wondering if this is useful for writing, say, something like a background introduction in the paper.
Maybe
Oh,
just like that. I think they just in this paper accepted last early this year. I don't know. But they just show that based on some general LLM model, they trained astronomy and they achieved the full level. I think that's the point. But I'm not sure if this really useful for real astronomy.
okay, 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 okay. I see.
So I think, but it's quite really improved compared to the previous model. This
So,
is these are previous model.
yeah, 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 yeah. I see.
I think it's too early to say this is useful for research.
Okay. But then for general use, maybe useful.
I think it's really useful for non-astronomers, I think. But still, maybe when we want to,
This is for professional astronomers. And ChatGPT or other things are not good for professional astronomers. That's why they are developing this way.
yeah, this is for astronomers, but
Yeah,
maybe
not-
it's
not
a little
for-
it's a little too early to use real scientific research.
Where do they say that? Do they say that?
I don't know. So that's why I say maybe. I'm not sure about that.
I mean, is that your opinion or it's written in a paper?
So it's my opinion.
Okay, based on what? Did you try this?
Uh,
Why do you say that?
Not yet. I didn't check anything. I just read this paper, and I just found the website here, but I think this is kind of beginning stage. So maybe we need some time to test, a little further test.
So the purpose, this is the development is, so that they can use it for research as well. And then, for example, you guys need to write introduction of your paper, right? This may be able to write it for you because they learned all these literatures, including the very latest ones. And then this is specifically trained for astronomy, not unlike ChatGPT. And then as Sonji showed, the score is better, right? And then, well, I'm not sure, but then they also mention carrying out data analysis, new research questions, developing new research questions, identify the new theory. These are things it might be able to do. So if you can use this, it might help research a lot. So actually, Sonja, I encourage you to try to use it. There is a source code available on the website.
So you can type the name of this model on Google and you can go to this.
No, I'm asking you to try.
I haven't tried this yet.
You do it right now.
Okay.
Okay, so I think it's time to move on to
Yes.
the second paper.
Yes. Okay. Maybe I can share my screen. Okay. Do you see my screen?
Yes.
Okay. Thank you. I think I posted this paper and also put it in this Excel sheet here. So actually this is not. I think the idea of this research is not very new, but then I think this was new to me. So therefore, this is interesting to me. And then this is probably related to the twins' work. She recently worked on FRBs to understand the baryon distribution in the universe. And then I think they can do the similar thing. They are presenting similar results using different methods. I think this method is actually, already established a long time ago. But anyway, so in this paper, so they use a quasar absorption system. Quasar is very bright. Then we can use this quasar. At a distant universe. So therefore, we can use quasar as a light source, and then light background, and then there should be material in the universe, say baryons in the universe, and then in foreground universe. So therefore, this quasar light comes all the way through the baryons in the universe. So therefore, baryon distribution should be imprinted in the quasar absorption systems, right? And then maybe interesting thing is they use only one quasar for this study. They select this quasar, actually redshift very low, or ratio 0.26, and then use spectrum data of this quasar. And then in this spectrum, so then there are a lot of absorption system, right? And then they try to use this absorption system and to relate this absorption system with the number of surrounding galaxies at different redshift. Because this absorption is happening along the line of sight to this quasar, depending on different redshift. So absorption system appears at different redshift. So therefore, across this, along this certain line of sight, they can investigate baryon distribution across different redshift. along the line of sight. I think this is the maybe uniqueness of this paper, this method. And then they selected one quasar which is along the line of sight to many, I think, galaxy clusters. They selected this quasar because this line of sight is intersecting multiple galaxy structures, I think, galaxy clusters. And then if I jump to the spectrum, so this is just an example. For example, I think this is easy to understand probably. This is really zoom in of high resolution spectrum of quasar. And then we can see some absorption systems here, right? So this absorption system is by alignment alpha. So that means this is a sign of neutral hydrogen at a certain redshift, because we know the rest frame wavelengths of alignment alpha. So therefore, using this observed wavelength of absorption line, so we can calculate what redshift is this absorber. And then using this absorption feature, they can calculate the column density of materials at that redshift. Then they use this kind of formula. So first of all, the width of absorption line is supposed to be, this broadening of absorption line is supposed to be because of temperature. So therefore, using this how broad is the absorption system, then they can calculate the temperature of material. So basically, this is a very high temperature. Say they say warm or hot gas, which is 10 to the 4 to 10 to the 7 Kelvin. That's basically ionized gas, but a very small fraction of gas is a neutral state. So therefore, they can still see the absorption lines from that. And then that's my understanding. And then they can also calculate this ionizing fraction here. And then anyway, so they calculate the column density or how much baryons are there for each absorption system they can calculate. And then in addition to that, there are so many figures, but I try to go to important image. In addition to this column density measurements, so they also know the galaxy distribution around this quasar position. This is, I think, quasar position. And then they have galaxy distributions here. So that means, and also they also know the redshift of absorbing material. So therefore, at each redshift of absorption material, so they can calculate how many galaxies are there around this line of sight quasar. And then they try to compare the amount of baryon or column density and how many galaxies are there at each redshift associated with the absorption system. And then it goes to, I think, one of this figure. I skip all the details, but probably, not this one. Oh, this one. I think probably this is important figure. So y-axis is this column density, so how many materials are there. And then as a function of number of galaxies around the line of sight, divided by number of galaxies expected from cosmic average. So therefore, basically this x-axis is, I think, the galaxy number density environment. How many galaxies are there at the redshift of absorbing material. And the y-axis is how much, say, column density you have for this absorption system. So then they found a clear, I don't know, correlation. They are saying there's a correlation between these two. So this means, I think this is almost the same thing as what Juin is saying. So if you look at the high galaxy number density environment, you can see more materials. This is appeared in by absorption systems in quasar sites. So that means if you look at the high galaxy number density environments, then you have more baryons in maybe intergalactic space or intra-cluster region, I think. So this is probably another way to present baryon distribution, I think, in intergalactic space. So I think that's all from this paper.
Okay, thank you, Tetsuya-san. Any question?
So, um, so I have one comment and one question. So this is neutral hydrogen, right? So I think it's a little different from Juin. And then my question is this over density, what scale did they measure this over density? And then did they discuss impact parameter?
I think so. I think so. But then, if I correctly understand, they have initial selection. I think they are only. Oh, wait, this is a reference paper. This one. I think they are limiting sample to this 30 megaparsec.
Okay.
Yes. That's. Then, wait a moment. Between cluster centers, how should we? Maybe this is a more practical constraint, I think. So I think they are considering line of sight within a structure within 5 megaparsec, I think.
Okay. So I was wondering there may be one more parameter here, impact parameter, because say if you have a same over density, say you have a galaxy cluster, but if it's right at the quasar place or a little bit shifted, then impact parameter is different, and then column density would be probably different. So
Yes.
so I would say if you consider this impact parameter, then the scatter on this plot may be reduced.
Yes. I think yes. And then sorry, Tomo-san, I forgot. I was initially thinking the same way. And then I think they are able to calculate impact parameter. Then, yes. I thought they present this somewhere. I'm sorry. Ah, これかなの、this is just an impact parameter as a function of red shapes, not as a function of density. But I think they have impact of parameter.
Okay.
Then, yes, and then I'm sorry, I forgot. Then let me read abstract. これ。But then, I think they have impact parameter, but probably they didn't include it in this last figure.
It's also interesting that if I remember correctly,
Yes.
for damped Riemann absorption systems, there was not clear correlation with the column density, I think. So I think a lot of people did it for DLA.
Yes.
But then there was no clear correlation like this. So it's interesting. I think DLA and BLA are looking at different systems, I think.
I think this is more like a diffuse diffuse gas, I think. So
So maybe DLA is more deeper in the galaxy. So
maybe.
okay, thank you. It's
Okay.
interesting paper.
Thank you. Thank you.
Okay, so I think it's time to stop. Thank you, three speakers today, and it's time to decide who will present the paper tomorrow. So tomorrow is Wednesday. So are there any volunteers?
So what can do that?
Okay, thank you.
So if you remember, the Thursday Hazmi-san is going to come. So if you want to present this week, please do it tomorrow.
Any volunteers?
Yuan and Kosas 3 times this semester. Good.
Maybe next week. I'm going to Japan.
You going to Japan?
Yes.
For robotics?
No. Oh, exam. GRE exam. Physics.
Why don't you go to robotics, Kyushu? Can you talk about Kyushu?
It's too
Hey,
far.
when are you going?
Tomorrow.
Tomorrow?
Yeah.
Oh, I didn't know. How about Terry? Oh, Terry, you only have 3.
Okay, so I can present.
Okay, good.
So tomorrow's Tomo-san, Yuan, and Terry. So thank you everyone for joining today, and see you tomorrow.
Okay. See you tomorrow. Bye bye.
Thank you.
Thank you, everyone.